Hello everyone, welcome back. In this video, I wanted to give a short introduction to polyprotic acids and their titration curves, and then I will dive into solubility equilibria. So, polyprotic acids will have a pH curve that have more than one equivalence point. Remember, the equivalence point is when the moles of what's in your beaker equals the moles of what you're adding from your burette. And so we're looking at examples of sulfuric acid and, phosphoric acid. That's a triprotic acid, so you would expect to see 3 equivalence points for phosphoric acid. And in this example here, you see sulfurous acid, H2SO3, titrated with sodium hydroxide. And so there's the first equivalence point, and then there's the second equivalence point. The first equivalence point represents the titration of the first proton. So basically, in this example here, it took about 25 milliliters to pull off the first proton with sodium hydroxide. And then the second equivalence point represents the titration of the second proton. So basically, when I say moles of what's in your beaker equals moles of your burette, you think of moles of what's in your beaker as like how much of what I'm titrating with is needed to pull off that one proton at a time when it comes to polyprotic acids. So if you're taking my class, then do not worry, you will not have a polyprotic acid titration curve. I wanted to just show it to you. Some of you may go on to take analytical chemistry, and you definitely will be working with polyprotic acids then, and using the skills that you've learned from my class for pH curves, titrations, for these more advanced topics. All right, so I wanted to begin with solubility equilibria now. Now, if you remember from first semester general chemistry, you would have learned some solubility rules. It's not for everything, it's just for the common ionic compounds that you work with and whether or not they're soluble in water. So for example, you learn that all sodium salts are soluble in water, there's no exceptions, but you would have learned like with sulfate, if it's paired with strontium, barium, lead, or silver, calcium, then those compounds are, quote, insoluble, and so on and so forth. So like I said, this is not a very comprehensive list, but it was good enough for first semester general chemistry and the ionic compounds you were working with there. However, now that you have a better understanding of equilibria, yes, you might say that things are insoluble, but it's insoluble to an extent. So let's look at an example here. We have calcium fluoride, which isn't on this list, but would technically be considered insoluble. But it does dissolve a little bit into ions when it's put into water. Not a whole lot, which is why we're using the equilibria arrows. And there is an equilibrium constant associated with this solubility. And so it's called KSP. SP stands for solubility product. And once again, it's products over reactants. And so this one's equal to the concentration of the calcium ions times the concentration of fluoride to the second power. Now we do not divide by the solid over here. Remember, solids and liquids are never included in the equilibrium constant expression. All right, so this actually, if you were to look this KSP up, it is 1.46 times 10 to the negative 10th. And therefore, it's really, really small, a lot less than 1. So yes, indeed, it does favor the reactants, in this case based on the equilibrium constant. However, once again, there's a small amount of these ions in solution. And something that's very common for these types of problems is to calculate the molar solubility, to determine, well, what kind of concentration of solution can I prepare that is soluble enough in water before I exceed the saturated solution. So the molar solubility is the number of moles of a substance that can be dissolved per liter of solution. It's usually in units of molarity, moles per liter, right? So units of molarity. And whenever you do your Rice table, it's equal to X. Because these particular equations are normalized, so the insoluble solid is 1. So if you solve for X, that gives you an idea of like, okay, that's the molar solubility of that quote insoluble solid. And when I say quote insoluble, what I'm saying is that solubility is on a continuum. It's on the spectrum, right? Where it's like, it's not just soluble and insoluble. Like some things are actually considered slightly soluble. So that's where, you're learning now that we can quantify that. We can quantify the actual solubility. And, for all intents and purposes, like calcium fluoride is definitely insoluble in water with a KSP value that's small. But once again, maybe we can make a dilute enough solution so that some of it dissolves before we go past saturation. All right, I just wanted to show you this table here. If you're using our textbook and you're in my class, that in the back in the appendix, there's a whole list of KSP values for all these different ionic compounds. And you can see some are a little bit more soluble than others. There was one that was like to the negative 39th for barium phosphate, right? So just wanted to show you that those are there. You'll use those to do your homework problems. For assessments, I would have to provide the KSP values for you. So in general, the solubility of an ionic compound is lower in solution containing a common ion than in pure water. And we're going to talk about why that is using an example. So let's continue on with calcium fluoride. Let's calculate the molar solubility of calcium fluoride in pure water. So first, we will need to write down the reaction of it dissolving into its ions. We're using a rice table because this particular solubility is in equilibrium. It doesn't go completely forward as sodium chloride would in a lot of cases, right? So we don't include solids or liquids, so that's why I'm kind of marking those out there. We didn't initially have, if we're in pure water, we don't have any sort of common ions there. Very negligible amount of calcium or fluoride, and usually you're working with deionized water for that purpose. And it increases by plus x plus 2x, and then 0 plus x is x, 0 plus 2x is 2x. So please be mindful. I know that a lot of the equilibria problems we worked so far are all 1 to 1 to 1 to 1. A lot of those acid-base reactions where only one proton's transferred at a time. Please be mindful of the stoichiometric coefficients. Don't forget about that, especially in these problems here where it won't always be a 1 to 1 mole ratio. All right, so let's go ahead. We want to calculate the molar solubility, which is just essentially find x. And so we have to set up the KSP expression, products over reactants, but not including reactants this time because it's a solid. Always be very mindful of parentheses here. Sometimes I see students drop parentheses, and so they would have kind of converted this to 2x squared instead of being 4x squared. In the end, it turns out to be 4x cubed because we have to multiply that by x, but just a common error I've seen before in the past that I want to make you aware of so you don't make the same mistake. So when we calculate x, it is equal to 3.32 times 10 to the negative fourth molar. And this is the molar solubility of calcium fluoride in pure water. So what that means is that if I made that concentration of solution of calcium fluoride in water, and let me fix this here. I forgot to put my, I forgot to put my 2 right here for the calcium fluoride. So if we were to make calcium fluoride in pure water at this concentration, then we kind of reach saturation. Anything more concentrated than that, and we would see calcium fluoride precipitate out of solution, or sometimes I like to say crash out of solution. So yes, once again, this is a very dilute solution, which really indicates furthermore that calcium fluoride is just not that soluble in water. All right. Now what happens if we prepare it in a solution that actually has a common ion in it? So let's do that example together. Let's calculate the molar solubility of calcium fluoride in 0.1 molar sodium fluoride solution. So something to make note of is that we understand sodium fluoride. All sodium salts are soluble in water. So when I put that salt in solution, it dissociates completely. Notice how I use the arrow going forward. It dissociates into the sodium cation and the fluoride anion, and the common ion that we have between the two salts is fluoride. Okay. So we're still calculating the molar solubility of calcium fluoride. So that's the rice table you want to do. Anyways, you wouldn't want to do a rice table of sodium fluoride because it's not in equilibria, right? It completely dissociates. Sometimes I see students when they work these problems, they start working with this equation here, trying to figure out the molar solubility. But remember, it has to be the molar solubility of calcium fluoride. So that's the reaction you write down on your paper. So calcium fluoride. This one's the very insoluble salt. And the rice table here. So initially we have 0 calcium ions in solution. That's not the common ion. But what we do have when 0.1 molar of sodium fluoride dissociates, that's a 1-to-1 ratio. We then have 0.1 molar fluoride ions in solution. So then over time, calcium changes by plus 1x, fluoride is plus 2x, 0 plus 1x is x, and then 0.100 plus 2x for the fluoride concentration at equilibrium. Now we want to figure out what x is. That's the molar solubility. That's our goal here. And that is equal to the concentration of calcium times the concentration of fluoride to the second power is equal to 1.46 times 10 to the negative 10th. This is equal to x times 0.100 plus 2x squared is equal to 1.46 times 10 to the negative 10th. Now, considering that KSP is such a small number, and the initial concentrations are actually pretty significant here in comparison, greater than the KSP. X, in a lot of these cases, is small enough to ignore, just because those KSP values are so tiny. There's not going to be a huge change, right? So I'm going to ignore plus 2x to make the math a little bit easier. And when I do so and solve for x, I get 1.46 times 10 to the negative 8th molar. And so this is the molar solubility of calcium fluoride in 0.1 molar sodium fluoride solution. All right, so if I were to make this concentration in 0.1 molar sodium fluoride solution of the calcium fluoride, then if I go any more concentrated than that, I'm going to start seeing some precipitation happen. Whereas you noticed how in pure water, the molar solubility was 3.32 times 10 to the negative 4th. So I'm able to make a more concentrated solution in comparison to the one with a common ion. So calcium fluoride is about 20,000 times more soluble in pure water than in 0.1 molar sodium fluoride solution. Why is that? I always ask, why? Well, the reason why this is because of Le Chatelier's principle. And the common ion effect. So basically what's happening here is that we've increased the concentration of the fluoride ions in solution. Wrong equation. So we've increased the concentration of fluoride ions in solution for the calcium fluoride equation here. And in doing so, we know that that shifts the equilibrium to the left, back towards reactants, and therefore decreases the solubility of calcium fluoride in the solution itself. So always think about here, if you're thinking about adding a common ion, remember Le Chatelier's principle, and that when you make a disturbance, like for example here, if you make a disturbance, you increase the concentration of a product, then the equilibrium will always want to restore itself. So it will go back towards reactants here so that it can restore that equilibrium from that disturbance. And also one final note, I know I mentioned with molar solubility that it's always equal to X. And that's because the salts are always normalized to 1. And so basically X represents the extent that 1 mole of calcium fluoride can dissolve in that particular solution. So that's why it's always X. And not like, for example, if we had 2 here, then, that'd be like 2X, for example. But it's always normalized to 1 for the salt. All right. Thank you all for watching, and I will see you next time.